Excellent. Okay, I make that the hour. So let me say welcome back, everyone, or welcome to anyone who's joined us fresh for the third and last lecture on today's second day of the 2026 Ising lectures. It's my great pleasure to introduce for this Ferenc Iglói from the Wigner Research Center in Budapest and the University of Szeged in Hungary, who will talk to us about disorder and order in quantum systems. Please go ahead.
Thank you very much. It is a great pleasure to speak in this very prestigious lecture series devoted to Ernst Ising. I thank for the organizers, mainly for Jurko, who invited me for this talk. Okay, let's start now. Just a minute. I try to... Okay, so this is a map, what you see, which is more or less contains the Austro-Hungarian monarchy, not completely, but most parts. And if you can check it, you can see the most important places which could be connected with this year Ising lectures. Here at the north, you can see Lviv. At that time, it was a part of the Austro-Hungarian monarchy and has the name of Lemberg. It was the German name. You can see actually here, so it is a map taken from a Hungarian side, so it is quite a few words are in Hungarian, so it is Hungary. You can see here is Austria. Okay, so you can see here is Linz, here where Reinhard, I guess, is sitting now. Here is Beach, which is Vienna. We just saw the previous talk from Jan from Vienna. And somehow you can here is our capital is Budapest, and here this city is Szeged. And as you noticed, my second affiliation, or where I am doing my teaching, it is the University of Szeged, which is at this place. Actually, Szeged is a somewhat smaller city than Lviv, but when I visited Lviv in 2008 in this Bogulyubov memorial lectures, I was able to visit a bit the city, and I noticed that the theater, the railway station, and the official buildings are very much similar than we can see in Szeged, let's say. So I guess that in that time, let's say, all the theaters in the Austro-Hungarian monarchy were more or less built with the same construction. So it is some way quite close, but I think in Vienna we can see also similar but much larger. Of course, this was the big capital, or one of the capitals of the Austro-Hungarian monarchy. Yes, if we go back to the universities, we know very well that in Lviv there were very prestigious professors during the old and recent times. I just say a few words, like Banach was, as far as I know, a professor. There's Smoluchowski, one of the very important personality in stochastic systems. Then we know that Ulam was also, as far as I know, also a professor there, and there is a long list of professors that we could say. If we then go to Szeged, here also we can find a few good names. Albert Szent-Györgyi won the Nobel Prize for Medicine in 1937. The mathematicians were also quite well known. I just mentioned Alfred Haar. If somebody knows the Haar measure, it is from this guy actually. Then Friedrich Ries, he was a guy who was very important in the functional analysis, or Lippold-Feyer for his theorem about this trigonometric series and summations. So these were here. And also a guy who gained the doctor title in Szeged was Cornelius Láncos, who actually is known, perhaps somebody who tried to diagonalize large matrices, and this is the Láncos method. Actually, one at the auditorium near me, I am now in Szeged actually. So near me is named after Cornelius Láncos. And if we go to the more recent scientific history, then we can say that two recent Nobel Prizes are given to former students of the University of Szeged. One is Katalin Karikó. She received the Nobel Prize in Medicine in 2023 for the mRNA studies, which was important for the COVID vaccination. And last year, László Krasznahorkai received the Nobel Prize of Literature. And all the both, they started their university studies in Szeged in 73, actually. I also studied here. I started my studies in 72. So very probably we already know each other at that time, at least could see each other in the Mensa or some other possibilities. Okay, let's go back to this map. And you see here actually here I prefer, I said that Cornelius Láncos also received his doctor title in Szeged, and perhaps somebody knows that he was an assistant of Albert Einstein. And now one might ask the question if Einstein ever has visited Szeged or not. We have no definite answer for it, but we know that he visited this place here, which is with this circle denoted, this title, which is now belongs to Serbia. At that time, it was a part of Hungary, of the Austro-Hungarian monarchy. And this was the place of his wedding with Mileva Maric, his first wife. And she was from this place, and perhaps you know that Mileva was the first student, lady student in the Zurich Polytechnicum who could enter and make the studies. Actually was the classmate of Albert Einstein. And there are negotiations that how important was what was her mathematical knowledge in some of the results which Einstein has received in the earlier papers. Okay, so much about Szeged, so much about Einstein and his life, and let's go on and let's see that what I am going to speak about today. What is the structure of my talk? I will speak about phase transitions in quantum systems in the presence of disorder. I start my talk with some experiments, some motivations which are connected with these experimental facts. And I show different types of fluctuations which could be important: thermal, quantum, and disorder fluctuations. Then I go to the main model what we study. So if we have the Ising lectures, it is of course should be connected with the Ising model. So it is the random transverse field Ising model as we will use it. And then the way of study is the strong disorder normalization group, and I will make some explanation about this method and the main results. I plan to have this part of the first part of my talk, which is planned for today. And for tomorrow, I will mainly speak about relevant perturbations, how long-range forces, many-body interactions, longitudinal fields will change the results what we have today and close by a conclusion. Okay, let's go on and look for the critical systems in general. The best known critical systems are thermal systems, and the first study of thermal systems was done by Charles Cagnard de la Tour, a French nobleman, in the beginning of the 19th centuries. You can find a nice piece of paper from Bertrand Berge and Malte Henkel about these studies, how he can then may quantify this transition. This is well known about the critical opalescence, which is presented somewhere here. Due to the long-range correlations, the the light scattering has such an opalous form due to the large correlated clusters what is formed at the critical point here. So this is the thermal fluctuations, and by studying it, we get the answer or as the phenomenon of universality. So in this case, if we use different types of gases, like neon, argon, krypton, or neon, oxygen, and so on, and we measure its phase transition temperature, and at the same point, the density of the system, and we rescale by the critical temperature and the critical density, then all these points looks to fit to a scaling curve. So this is actually how the universality is seen in this case. And actually this curve can be described more or less with a fit of the beta exponent is close to 1/3 actually. So this it describes the way of singularity that we have around this point. And this critical behavior is connected with diverging correlation lengths. So the correlation function, which is described in this way, has a correlation function here, which actually diverges at the critical point in a way when delta is just the difference from the temperature, from the critical temperature itself, and nu is a corresponding critical exponent. At the critical point, these correlations have a power law decay as shown here, and this exponent, let's say the eta, is somehow is connected with the magnetization, and this one to the energy. So these are the two exponents which describes this type of system. The second problem that we consider when we can have also, besides the thermal fluctuations, also quantum fluctuations. For example, we have this lithium holmium fluoride. This is a dipole bonded quantumizing ferromagnet. So it means that dipole, so this is long range forces, and that's why the phase transition due to temperature belongs to the mean field universality class. If we have an external field and one studied low energy behavior of the system, one can show that there is a doublet which will be splitted by the square of the strength of this magnetization. So actually altogether this at the low temperature behavior will be described by this transverse field Ising model, where the sigma x and sigma z are the Pauli matrices. Without this term, we have the normal classical Ising model, and this one is the extra, this is the transverse field in the system. And if we follow the phase diagram of this system, then we see that the para and the ferromagnetic phases are separated by a phase transitional line here, which actually goes to zero. And here the thermal fluctuations are out, and we have just quantum fluctuations due to actually this the combination of these two terms. So the quantum fluctuations are due to the fact that the different components of the Pauli spin operators do not compute. So that it makes then the quantum fluctuation. So we are interested what kind of a phase transition takes place in this system, or altogether what is the phase transition along this line. To answer to this question, we can use a quantum classical correspondence. So actually here is our, let's say, a one-dimensional chain for the simplicity, in which this is the coupling and this is the transverse field strength. And now using either the Feynman path integral formalism or the Suzuki-Trotter type of calculation, then actually we will have a d plus one dimensional system. This is a classical system where the extra the dimension is the imaginary time here. Actually, the extent of the system in this imaginary time direction is connected with the temperature. Actually, it is with the inverse temperature is given. And the question how this system behaves when we approach the critical point. If we are at finite temperature, then actually this width of the system is finite. So it means that the quantum effects are just finite size corrections, but the critical behavior is the same as for the d-dimensional classical system. However, if we go to t equals 0, when the width of the system is infinitely large, then we will have a d plus one dimensional system which have a different type of critical behavior. Actually, there is a relation between the spatial extension and then the imaginary time extension. Between the two, the relation is given by this dynamical exponent z. It is known that when the system is homogeneous, that this exponent is just one. So the critical behavior of a pure quantum system is just the same as the d plus one dimensional classical one. Yesterday, Reinhard just made an example for this in the two-dimensional case. However, if we have disorder in the system, so which means that this coupling and this transverse field are position dependent, then the corresponding classical system will be a strip random system where they have the same values along this column or in this strip, but these are different from strip to strip actually. This type of system, which in two-dimensional has been studied in detail by McCoy and Wu and others, it is known that in that case, the dynamical exponent will not be one, but something different. And this is actually a basic question: what is going to happen in this system if we have also a disorder? Okay, and how we can have in an experimental system disorder? We choose the previous example, the lithium holmium fluoride, and we replace a part of the magnetic holmium ions by non-magnetic yttrium. And this will mean that actually we replace our Hamiltonian, which is here, by this term which contains this randomness or this irregularity. Here you can see actually the atomic system size. So here is the holmium, which is replaced by the yttrium. And then in the system, due to the disorder, the critical behavior will be, okay, sorry, the critical behavior will be changed. And as the experiments shows that the paramagnetic and the ferromagnetic phases will be accompanied by a third one, the spin glass phase. So this is the spin glass phase. When this temperature goes to zero, then actually this will be a quantum spin glass, which can be seen actually in this case. So, and the question could be, what is the properties of this system in which the quantum and disorder fluctuations are present, or also at finite temperature we have also some thermal fluctuations. So this is also a next question. Now let's go on and see another example in which we have quantum and disorder fluctuations at the same time, and these are the Anderson localization. Actually, we choose this problem in 3 dimensions, where there is actually a localized Anderson localization transition. Originally, this problem was treated in metals by Anderson, but it is more interesting. It can be visualized more clearly with cold atoms experiments, which was made quite recently. So actually, here is this is made, I guess, by several groups, but the aspect group in Palaiseau in near Paris made this. Saclay made this experiment. So here, actually, you can see this experimental setup. Here in the center, you can see the cold atoms, which are rubidium or cesium atoms. This magnetic these magnets will keep it in this position here. These are paramagnetic and could take it in a given position. And 2 lasers are used to irradiate this sample with spectral lasers, which means that the interaction is random somehow. So having some glass which is not homogeneous, but having different type of disorder on it. So it makes such a spectral laser source, and this will then show this random potential which is here. And then you put all these atoms in one position and look its evolution after keeping it in time. And actually, depending on the strength of the disorder, which is actually with the strength of this laser field, the following transition can be seen. If the disorder is sufficiently weak, then the system, then the wave function will be extended. So in time, if you measure it, this can be measured by fluorescence spectroscopy, for example. And one can see that this will be moving. So these atoms will not stay at the same position, but more or less move classically. So these are the extended wave functions, which can be visualized here. If, however, the disorder is strong, then one can see that for several seconds they will keep their position, and you see that the seconds in the life of these atomic systems here, where the usual time scale is 10 to the minus 13 or something like this, is enormous. So actually these are really localized. So this is another problem which contains at the same time quantum and disorder fluctuations. And the last problem where quantum and disorder fluctuations are present is this is the two-dimensional superconductor insulator transition. In two dimension, it is known from the Anderson localization that the electrons in this case are always localized. So actually it should be always insulator and cannot be a conductor. However, it can be a superconductor in this case. And this transition takes place as the disorder is somehow increased. So you can see here that this is the resistivity. In this type where this is superconductor, this goes to infinity actually. And this is when the width of this bismuth is sufficiently large, so the disorder coming from the surface and it could influence the wave function of the system is not relevant, and so it is in that case it is a superconductor. However, if this will be thinner and thinner, then actually there will be a transition, and here you see that this resistivity actually diverges. So as it takes place, as the temperature goes to actually zero, so this is the insulator, and in between there is actually a transition. A similar transition can be made if external magnetic field is used in a similar way. Okay, so that's all what I wanted to say about the experimental background. And let's go on and take the basic model that we are going to study. And as I mentioned, this is the Ising lecture, so it is the random quantum Ising model. But as you all know, the Ising model is very much a very important model actually, not only in classical magnetism, but also quantum systems, also in all type of ordering phenomena. We heard yesterday about the cities, today about the entropy, tomorrow also some other application. So in my case, this is the random quantumizing model. Actually, it has the same type of Hamiltonian as I showed before with this lithium, holmium, yttrium system. Just here I use nearest neighbor couplings. So this is the easiest version. In the experimental one, we had long-range forces. Here, this is just the basic one with the nearest neighbor forces. And we use the couplings and the transverse fields. They could be, usually both are random. And these are the Pauli matrices, as I mentioned before, with the X and the Z component, and the quantum fluctuations are due to the non-commutativity of these spin operators, the different components of the spin operators on the same position. Okay, and we are interested in the properties of this system. And actually, if we are looking for it, here we can see some illustrative phase diagram. Here, this delta is the control parameter, which is the difference between the average log transverse field minus the average log log coupling. So actually, if the transverse fields are larger, so this is the disordering effect. How is it? Yes, this is the disordering effect. Then the system is in the disordered phase. If the couplings are in average larger than the average transverse field, then we are in the ordered phase. From the point of statics, we can consider the average magnetization, which actually in the disordered phase, it vanishes exponentially, where L is the linear size of the system, D is the dimension. In the ordered phase, this actually has a value of order 1. And at the critical point, it vanishes as a power with this exponent x, which is the anomalous dimension of the magnetization, actually. Okay, it is interesting to consider the dynamics of the system, how the energy gap and the related quantities behave. And this is the following, that actually in the gap in the system, in the disordered phase is usually of order 1. However, here we have a so-called Griffiths phase. In this Griffiths phase, I will speak a few words later. Still, it is this energy gap will goes to 0 as a power law with an exponent z, which is the dynamical exponent, which depends actually the position here. And actually, if we approach the critical point, this exponent z is increasing and actually will be divergent, and here we will have an unusual type of dynamical scaling, where the lowest gap goes to 0 as exponential to the L to the power of some quantity psi, which will be an important exponent here. When we are in the ordered phase, then this gap closes actually exponentially. Okay, and let's see what is going to happen in this Griffiths phase. So this is just a peculiarity of the random systems that you can have. So here is some visualization. Here we are in the disordered phase. And let's consider that we have a bimodal distribution of the couplings. So there are strong and weak couplings. And actually, the transverse field that we have is larger than, let's say, that the middle value of this, or the value which is needed to be at the critical point. So if we have a larger value of this transverse field, then we are in the disorder, in the paramagnetic phase. However, this field is not larger than the largest value of the largest couplings. So then there are clusters in the system in which there are strong couplings accumulated. And these strong couplings will change the dynamical behavior of the system. Actually, these are rare regions, since to have actually one is a strong one, it is probability 1/2, 2 it is 2 is it 1/2 to the power of 2 and so on. So it's exponentially small with the size of the system. So this probability is given by this exponential form. However, the excitation energy to create such a object, starting from the disordered one, you see that you should actually make an excitation and turning all the spins, actually V-type spins from down to up. And this actually will be made by a perturbation calculation of V's order, actually, since you have to turn one to the next and next and next. So it is quite a small energy that you can have. So it is also exponentially small in this case. So this is if you combine these two, so you express from here the V, which is log epsilon, put here and calculate this distribution, you will end up with a power law distribution of the energy scales. And actually, if you then use this distribution for the specific heat, for the susceptibility, for the magnetization, and for the entropy, you always will have some type of a power law dependence, which is actually means a semi-critical behavior for dynamical properties of U. You have in that respect a critical behavior in the facts that we can have here. So this is valid actually in this region that I show here. Okay, and the next point, in which way we can study this system theoretically. It turned out in the early days that the epsilon expansion does not work. It gives divergent results. The quantum Monte Carlo simulation is a possibility, but quite time consuming, and you cannot go usually to very large systems. And the way that is a good way to study it is a version of the renormalization group, which is called the strong disorder renormalization group. And we are going to describe this in the following transparency. So actually, this strong disorder renormalization group was invented sometimes in the end of the 70s of the last century. So you remember this was the time when the critical phenomena was very, very popular. In this decade was published by Wilson Nobel Prize papers, plenty of type of renormalization, real space renormalization group, other epsilon expansion, others has been invented. And Ma Dasgupta and who studied this system, or not really this system, but this random Heisenberg chain, and with very similar techniques. And this type of method has been used then later by Daniel Fisher to make the calculation. Now, let's say, what is the essence of this renormalization group method? Here, this is, we consider the quantum and disordered fluctuations and treated at the same time. And actually, this renormalization is local and actually is made some way in the energy space, in a way that you take the parameters of this Hamiltonian and you consider that parameter to which the largest energy scale belongs. Actually, this will be the energy scale actually for which the time scale is the shortest. So actually, when you go to the critical point, this will be unimportant for the critical behavior at the critical point when the time scale also diverges. So, and this type of parameters will be eliminated. So in this way, the energy scale connected with the energy gap is reduced in each step. If, let's say, starting, this omega is denoted by the largest parameter, this can be either a coupling or a transverse field. If it is a coupling, and actually it is a very large coupling, then these two terms will somehow be flipping coherently. And if you consider the energy scale of this doublet, of just of these two, this will contain actually four states, which are separated by this energy scale here. And when this energy scale is very large, you can omit this the upper two energies. You keep these last two, and this will actually just be one composite spin in the space of a renormalized transverse field here. And the value of the renormalized transverse field is calculated in second order perturbation calculation. In second order perturbation calculation, you have here in the denominator these matrix elements, which are the matrix element for the two H's, which are the Hij, the product of two, divided by the energy difference, which is here. So you replace by this. If you have the opposite situation, that the largest parameter is a transverse field, then this transverse field is so important actually that it will flip out this side. And if one has some longitudinal field to measure the susceptibility, this site will not contribute to it. So you can eliminate this site, and actually you calculate the effective coupling between these two remaining sides. And if you make this and use actually the duality of this chain, you will just simply replace couplings and fields, and you get this rule. And actually by this you will at one step reduce by 1 degrees of freedom of the system, either a coupling or a transverse field, but you will have the same chain. And actually you can then write down integral differential equation about the distribution of the couplings and the fields. And it happens that this type of calculation can be made analytical in one dimension when this topology is survived. And this was Daniel Fisher who made an analytical solution in one dimension. And at the fixed point, this solution shows that this is a infinite disorder fixed point, which means that this generated new parameters what you have. So you repeat this calculation further on, and then until you will reach or approach the energy scale to zero. This means that actually the time scale is divergent, so you approach the critical point of the system. And at this point, one can show that actually the infinitely disorder means that if you take two neighboring parameters, then the ratio of these two will be either infinite or zero. So these are completely different, which actually will mean that the second order perturbative calculations at the fixed point, at the critical point, became asymptotically exact. So in that respect, the results will be also exact. And as a result, we know actually that for this random transverse field Ising model in one dimension, we have practically more exact results than about the homogeneous version, which is equivalent to the Onsager two-dimensional Ising system, in the sense that here some distribution functions and other quantities are also known analytically. So this is actually the way what we have in one dimension. And actually the next step is the question that what is going to happen in higher dimension. Now I asked the question that what to do. It is 45. Should I stop now and let people to ask questions, or continue for 5 more minutes? What is the decision?
I would be tempted to see if there are questions at this point, and if the field is thin, then take a few more minutes, but let's prioritize discussion if there is some. Therefore, thank you very much. That was a very instructive opening part. Are there questions? As before, please raise your hands or just unmute yourself. Yoko, please.
Yeah, thank you very much for very interesting story. I have a question with respect to parameter delta. You showed us phase diagram telling that all depends on delta, and basically it is difference between two averages, average of random H and average of random J. And I wonder, does the distribution function of H and distribution function of J, does this come into play or not? I mean, I can say that H is strongly correlated, is long-range correlated, and all this stuff. Presumably, we impose some conditions on the distribution of random variables H and J, right?
Okay, thank you very much. Actually, I did not say that. Actually, the H and the G are independent and identically distributed random variables. If this is the case, and how to say, if there is not two long-range correlations, that these are usually universal. So usually one expects that the form of the disorder, if the disorder is, as I mentioned, is independent and identically distributed, that it does not matter. And actually, you can see if the solution of the one-dimensional case, that at the fixed point, actually, this distribution that you have, it will not be dependent on the form of the original distribution, assuming this type of non-correlated behavior. If there are strong correlations, how to say, this should be extremely strong. So as you can see, at the critical point, you have this exponentially small gap. If it is correlated in a way that the correlation is also some way is made in exponential form, then you can actually change this one. But these are really quite strong correlations. For normal correlations, it is not the case.
Thank you. And may I put one more?
Please.
With respect to the region where the Griffith phase shows up, I know that when I'm speaking about thermal phase transition and say it is diluted magnet. So usually one says that this Griffith phase appears at the critical temperature of the pure magnet, and it survives up to the critical temperature of the diluted magnet, which is obviously smaller, right? And then comes this reasoning about islands of ordered spins, which are ordered because they are below the critical temperature of pure system. And now here from the space diagram, I see that the distance is defined only by the difference in these average values of H and J, right?
Actually,
here.
The actual position here, how to say it depends actually also the form of the Z itself. It depends on the specific form of the distribution of the field and the coupling. And actually the end of this Griffiths phase, as I mentioned, it depends which type of distribution you have. If you have a continuous distribution, let's say, then this will go to all the phase diagram actually. So it is unlimited. It is if it is not in this way, then there will be an upper limiting value. But actually, this Griffiths phase or Griffiths effects you can have also in the ordered regime and also in the disordered regimes, but these are somehow different.
Yeah, thank you.
Thank you. Reinhard, please.
I have a question which you might think I should know, but it is on this dynamical exponent set which comes in when you compare the quantities of a classical and a quantum mechanics systems. Now, if you have a spin chain, in fact, you have a system where the spin is a vector. And so you are in a universality class, which is not the Ising model, but it's a XY model or third order. So how is this treated, and how you find this in the relation you derive for these more random systems?
As far as I know, actually, just a minute, where was this? Yeah, I think, here was. Actually, I guess in this mapping, it's very probably important that you have a discrete symmetry of the spin, I guess. That I am not sure about it, but I think that the Z exponent is just equal to 1. I guess it is the case when you have a discrete symmetry. So if you have Ising, pots, or
it's not really a vector; it's just a
really
Q state.
If you have a Heisenberg model, let's see, then this is already different. As also the low energy excitations in these systems are different in this system. Yeah. So you are right. In that case, one needs a more distinct investigation. Yeah.
Okay. Thank you. Thank you.
Thank you very much. That has taken us slightly over time, so I propose that we'll close there for today. Let me reiterate our thanks to both of our lecturers, Jan Korbel and Ferenc Iglói. And my thanks to everyone who's attended and for their participation in the discussion. And the lectures will resume tomorrow at 3 o'clock Lviv time. Oksana, are you going to squeeze in a last photo before we go, or am I closing here?
Right, and before we do the lecture, I also want to add thanks to the chairpersons.
Oh, almost literally the least I could do.